Hi, and welcome to another episode from Spiral Physics Education. So in this lesson we're going to be looking at displacement time graphs, and we're going to be looking at those and describing the motion given some different shapes of displacement time graphs, and we're also going to be calculating the velocity from those. So all of those are very common exam questions at GCSE and IGCSE level. So to help you get the most out of this lesson, it would be really helpful if you knew about scalars and vectors, and also if you were able to confidently calculate velocity. And if you're not sure about either of those two, please do check out the channel because there are various videos to help you get up to speed on those. So firstly, let's have a look at displacement time graphs and the vocabulary that's used in them. So we call them displacement time graphs basically because we want displacement on the y-axis and time on the x-axis. Whichever physical quantity comes first, that's the one that we put on the y-axis. So displacement time, we've got y-axis, x-axis. And that's the same for all terminology that we use when we're drawing graphs. So we might have IV graphs, current voltage graphs, current on the y-axis, voltage on the x-axis. Velocity time graphs, velocity on the y-axis, time on the x-axis. So it's a very, very common thing to say the y-axis variable first and the x-axis variable second. So when we're drawing displacement time graphs, this is the sort of thing that we do, and this is the sort of thing at GCSE that you might see. So let's get on to looking at how we calculate velocity from this. So if we look at the gradients, what we're going to do first of all is identify a nice big triangle in our nice straight line graph here. So there's my large triangle, and I advise in exams to always draw the triangle and try to make it as big as possible. You make it as big as possible, uncertainties get smaller. So I'm going to identify two different dimensions of this. I'm going to call the bit that goes up vertically, I'm going to call that rise, which you might have heard before in maths or in your physics lesson. And the horizontal section of that triangle, I'm going to call that run. So we've got rise and run. You might have heard about dy by dx, or change in y over change in x. That's the same thing. So what we do need to realise is that when you're calculating the gradient is simply the rise of that triangle divided by the run of that triangle, or dy by dx. And that's going to be, if we look at it, the rise, well, that's displacement, and the run, well, that's the time for that displacement. And if we think about what velocity is also displacement divided by time. You can see that the gradient and velocity are exactly the same thing for these displacement time graphs. So to calculate velocity, we just calculate the gradient. So let's have a look at a very common exam question, and that is describing motion. So we get given various different shapes of displacement time graphs, and you're expected to be able to describe the motion by just looking at those shapes. So here we've got a straightforward example to start with. So what I'm thinking here is that the gradient is constant, and that means that the velocity is constant, and also the gradient is quite small, so that means the velocity is quite small. So for this object, it's moving at a slow, constant velocity. Let's have a look at a different example. Slightly different, but I'm still thinking, oh, it's a constant gradient here, so that must mean it's a constant velocity. It's also quite large compared to the other one anyway, so the velocity is larger. So it's moving at a large constant velocity. Okay, let's have a look at another one, slightly different again. Well, I'm thinking still a constant gradient here, so it's moving at a constant speed, a constant velocity, but the gradient is 0, so it's actually, its velocity is 0, or really, it's stationary. Another different shape, much harder to realise what's going on, but we can still adopt the same thought process. Here we're looking at the gradient. The gradient is increasing. That means the velocity is increasing. And we call increasing velocity, well, we call that acceleration. So the object It's just accelerating. If we look at a different sort of curve and think about the same process again, I'm thinking here the gradient is decreasing. Oh, so that means velocity is decreasing. What do we call decreasing velocity? Well, we call that deceleration. Well, this object is decelerating. Another shape is slightly different again. Same process. Look at the gradient. Well, the gradient here is constant. Well, the velocity is constant. The gradient is negative. Well, that means the velocity is negative. So what does negative velocity mean? Well, if I think positive velocity is in that direction, then negative velocity is just in the opposite direction, i.e. it's reversing. So it's moving at a constant negative velocity or a constant velocity in the opposite direction or reversing. So let's have a look at how to calculate velocity. And these step-by-step procedures here are very, very good to follow for exams. It's advisable to follow these step by step. So we've got given an example here, and we're going to calculate the velocity of this object. And we know that velocity is displacement divided by time, and that is actually equal to the gradient. So I'm going to identify a triangle. So here's my starter triangle. So that's my rise there. So the rise of my triangle is 12 meters, and the run of my triangle is 15 seconds. So I've got 12 divided by 15, which is 0.8. And don't forget the units. So slightly harder example question to do for an exam is describe the motion of this shape graph. Because it's got 3 sections in it, so try and make life easy for yourself. Break it down into 3 sections. There's a section from 0 to 5 seconds, there's a section from 5 to 12 seconds, and there's clearly a section from 12 to 15 seconds. So break it down. And when you'll get given a graph, try to quote data from the graph. I'll give you an example. So from 0 to 5 seconds, the velocity is constant. And I've also calculated it to show the examiner that I can do that, because it's quite straightforward, 16 divided by 5. From 5 to 12 seconds, the velocity is constant at 0 meters per second, i.e. it's stationary. And from 12 to 15 seconds, the velocity is also constant, but it's negative, it's minus 4 meters per second. So I could say there that I've completely described the motion of that graph, or that object from that graph, by breaking each of those sections down and trying to be as detailed as possible with the data involved. And we can also say that it returns to its original position because the final displacement is 0. Another common shape graph is this one, and students find this quite difficult to do as well because it's not a straight line. So what we can say is that the gradient is decreasing as time increases. And then we can say that that means that velocity must be decreasing as well. So we can also say then it's decelerating. We could also look at right at the beginning of the graph and sort of maybe try to estimate the initial velocity. So looking at that, maybe it's around about, right at the beginning, around about 4 meters per second. And right at the end, it looks like the gradient is going to be 0. So we could also say at the end, the gradient is 0 and therefore it's stationary. So it goes from 4 meters per second to 0 meters per second, and therefore it's decelerating. So we've got lots and lots of language and data there, so it's a very comprehensive answer to this question. So I hope you found that introduction to displacement time graphs useful. Don't forget to subscribe to the channel where you can find out more useful things about physics and hopefully improve your understanding in time for your exams. And I'll see you next time on Spiral Physics Education. Goodbye.